Hi, this is Gordon Parker from Michigan Tech, and in this video we're going to have some fun with block diagram reduction. And the motivation is control system design. So here's a motivating example. Let's say that we have this block diagram for some control system that we're trying to analyze, and actually perhaps we're trying to design this parameter k, some sort of gain, to achieve some desired closed loop performance. And the closed loop transfer function for this would be y of s over r of s. Now everything here is in the Laplace domain. Our signals, the input reference command r of s, the output y of s, all of these blocks have letter designators in them. These are really transfer functions, g1 of s, g2 of s, etc. They're irrational functions in general with a numerator and denominator, both polynomials in s. And then we have this constant here, k, that is our design parameter. And so the goal could be to find some value of k to make sure that y of s, the output, responds in some specified way to an input r of s. A couple bits of terminology before we get started is we call these points pick-off points. So let me draw an arrow down there and say pick off. So that just means that that signal tees off at that point into G1 and G2. Pretty straightforward. This is called the summing junction. And that allows multiple signals to combine. Here there's a couple summing junctions. This one has the signal R going into it and then subtracting the signal D of S multiplied by Y of S. And that's actually another important bit about block diagrams. One of the most basic elements of block diagram reduction goes like this. If we had some signal R of S and an output signal y of s, and then we have a transfer function here called g of s, then the way this works is this signal r of s passes through the transfer function and ends up here. So at this point we have r of s times g of s. And of course that is identically equal to y of s. Now this starts to look very familiar because we could rewrite this as y of s over r of s, which is g of s, which would be our transfer function. So that was the point I was trying to make here, is that we have a signal y of s. It moves along this path, passes through or is operated on by d of s. And so at this point, we can think of the signal as being d of s times y of s. And then that's subtracted from r of s to give this quantity that then splits off and goes in various places. Okay. So to summarize, we have a little bit of terminology. We have summing junctions, pick-off points, and then we have this most fundamental of block diagram reduction ideas. Well, let's do a little example, which is actually one of the most important block diagrams that you will ever encounter. And if my pen can work, there we go. So we have some input R. I'm going to leave off all the S's now that we've gone through this little introduction. Goes into some transfer function G, and then out pops a Y. And then we have a pick-off point, some feedback. It's always nice to have feedback. And that goes into this summing junction. And I'm subtracting them. Okay, so if I were to analyze this block diagram, I can do it using what I would call a brute force approach. I'm going to switch colors and actually make it kind of a thick line. And what I'm going to do, I'm going to mess up this block diagram for you, but what I'm going to do is I'm going to start here and I'm just going to march through in that direction of this block diagram. And along the way, I'm going to tally up all the different signals I have. So let me get rid of this line now. And I'll leave it in red. So at this dot, I have R, of course. And then right here, what I have is R minus YH. Right? So we have R minus YH, which is right here. That whole thing passes through the block G to this point, then I would have G times the quantity R minus Y H. And of course that is identically equal to Y because I'm sitting there at the output. So if I multiply that all out, I get GR minus GHY equals Y. And I can now solve for the closed loop transfer function. I can throw that negative GHY to the other side and solve for Y over R. And I get G over 1 plus GH. That is probably the most famous closed loop transfer function you will ever encounter. Now in general, what we can do is rewrite this block diagram above like so. Put a G in there. Here's Y. And I'll bring the H as feedback. And what I'm going to do is change what I have in the summing junction. I'm going to write this as minus plus, which just says that I'm drawing this one block diagram to consider both situations where I either have negative feedback or positive feedback. And then Y over R will similarly be able to have two different scenarios that it handles. There we go. So if we have negative feedback, then we pick the positive sign in the Y over R transfer function. And if we have positive feedback, we get 1 minus G times H in the denominator. Okay, so that is that example. And now let's go ahead and do some block diagram reduction formulas or ideas. So I'm going to switch back to black. And the first thing that we'll do is a couple easy rules. So 2 easy rules. And what they are considering blocks in parallel and blocks in series. Let's do the series one first. So if we have some signal R and it goes into G1, and G1 is in series with G2, then you can simplify this block diagram down to, I bet you imagine what this is, G1 times G2. Easy stuff. Parallel blocks go like this. If we have R again going into G1, and we also have R going into G2, and then finally we sum those signals up to make Y, then we can simplify this down to G1 plus G2 going into Y. And you can memorize this sort of stuff, but you can also just work your way through it, right? If you take this parallel scenario, you have R times G1. So if you look at this spot, you have R G1. And if you look at this signal, you have R times G2. And then we're just adding them together to get Y. And sure enough, that's exactly what you would get here. You'd say that Y is equal to R times the quantity G1 plus G2, which is exactly the same as, of course, RG1 plus RG2 that we would get in this case. Okay, so now we have the 2 easy rules. We have that very famous, sometimes it's called the canonical block diagram form. So we have a lot of basics down. Now let's do a couple of the more interesting block diagram reduction techniques. What we're going to do first is we're going to move pickoff points around blocks. Okay. And just barely squeeze it in there. So let's do the forward case first. So what we'll do is we'll have a block diagram with a pickoff point in front of some transfer function. And here it is, and we want to move it to the other side of that transfer function. This happens quite a bit when you're doing block diagram reduction graphically. A good foundation to get started with this is to write out the expressions for both y1 and y2. So y1 is equal to r times g, and y2 is just equal to r. So now we know what we're looking for when we move this pickoff point to the front side of G. So here's our y1. I'm moving it right to there. Then we had better end up with the same expressions for y1 and y2. So here I'm going to need to put something in order to get my y2. Let's start working on y1, which is just r times g. That checks. Fantastic. Right now, if I look at this point, of course I still have r times g, but what I really want is just r, so what needs to go into here is 1 over g. So that's how it works. If you move this pickoff point to the other side of a block, you have to make sure that you insert a new block and stick into it 1 over the block that you moved around. Okay, so now let's do the moving the pickoff point backward. And I'll abbreviate backward like that. So let's start with this block diagram. So we have our y1, and we'll have a pickoff point there and a y2. Again, just to get our bearings straight, we can see that y1 is equal to r times g, and y2 is just equal to y1, so that's also equal to r times g. So when we move this pickoff point back to there, we need to make sure that we still get those expressions. So let's just start. Here's r. I've just now moved the pickoff point. There's g. Here's y1. And I'm going to go like this. I'll draw an empty block there for now and start doing this little check. So y1 is still equal to r times g. Fantastic, that checks. And what do I need to stick into this block? Well, it's pretty straightforward. I just need a g. So then y2 is also equal to r times g. Okay, so in summary, if you move a pickoff point in front of a block, you just have to make sure that you take that signal, add a new block equal to the block that you hopped over. No problem. It all looks easy when you're doing it like this, but when it's in the middle of a big complicated block diagram, it gets a little trickier. Okay, so the next thing we're going to do is move summing junctions, right? So we've kind of exhausted the pickoff point issue, and now we're going to move to moving summing junctions. Let's do the forward case first. So what we'll do is draw a example. So we have some input signal R1 and another input signal R2. They are added together and then they are get operated on by G. So Y is equal to R1G plus R2G. Okay, so now when we move the summing junction over to here, we just have to make sure that we still end up with that relationship. So let's go ahead and do it. We have our R1 goes into G and then into the summing junction that's been hopped. There's our Y, and here's our R2. I'm going to draw an empty block going into there, and then we'll try to figure out what needs to go into that empty block. So at this point we have Y is equal to R1G, and then we have an R2. This also needs to have a G in it. Okay, in order to make sure that our Y in these two cases are equal. Okay, so the moral of this story is if we move the summing junction, hop it forward through a transfer function, G, then we need to insert a new block equal to that value that we hopped over. Well, now let's move a summing junction backward. So here, I'll abbreviate it like that. Let me draw a quick picture of an example. So here's our transfer function G, and here's an output Y. Here's the input signal, and we'll sum that with, we'll call that R1. We'll sum that with another input R2. Great, so y is clearly equal to r1g plus r2. And so that's the relationship we need to have hold when we move this summing junction to the front side. We're sort of moving it backward, hopping it over a g. So let's go ahead and start drawing that out. Here's our R1. We'll just move that summing junction. And here's our block G. And there's our output Y. And we'll also have R2 coming along. And we'll stick in a blank block for now. We'll add those up just like they were in the previous block diagram. And so now let's start putting together the pieces that we have. We have R1 here moving through G. So that's good. That's good. That's that part. But now if we just take R2, it would also go through G, and we don't want that, so we'll have to divide through by a G here to get plus R2 over G times G. And so the G's cancel, and we get exactly what we need. Okay, so that's it for moving summing junctions. We just did moving pickoff points. There's really just one other thing I want to show you before we do a quick example. Let's say that we have a summing junction that has 3 signals going into it. Right? All the examples we've looked at so far just have 2 signals, but we could certainly have as many as we'd like going into that. And you just have to stay a little bit careful. You have to take some care when determining which plus goes with which signal, but it's usually not too hard to figure out. So of course y is just equal to the sum of the r's, so r1 plus r2 plus r3. And what I want to show you is that we can take that scenario and break it up into as many summing junctions as we see fit. So let's say we want to break that up into 2. Here's our output y. Let's say we have r2 coming in there and r1. Sum those up, and then that sum goes into this summing junction with r3. That pops up quite often when you're trying to do block diagram reduction. Okay, so we've got all of our rules, we've got some background, some terminology. Let's do a real simple example, and there'll be another video posted that has a more complicated example that covers all of the different rules. But this one will just be to get us started. So let's say we have some input R, and it goes into G1, and we'll have that come down here. Let's also tie off from R and have it go into this summing junction. So we'll add those 2 up. And let's take that output, throw it into another transfer function G2. And how about another summing junction? And let's grab this, another pickoff point, and go all the way to there. And we'll subtract that just for fun. Finally, we have G3, and that goes to our output. Okay, so let's try a couple things. We'll add some things up, move some summing junctions around, and get a closed loop transfer function. So what we're after, not to lose sight of the prize, is our closed loop transfer function y over r. And actually, this one you can kind of do by observation, because if you look at these 3 paths, let me switch colors. I think of this as one path, that is another one, and that is another one. If you follow this path all the way through, you can see that you'll have a component of y that's equal to r times g1 times g2 times g3. And then along this path, you'll have, well, I can actually write that down, r, g1, g2, g3. So that would be from this path. And then from this path, we'll have plus r times a g2 times a g3. And then from this path, we'll just have a minus r g3. Okay, so let's go ahead and switch colors. Okay, so let's do this through block diagram reduction. The first thing we'll do is let's let's move this summing junction to this side of G2, because if we do that, then we'll have this block in series with G3, and so that is something that we can work with. So let me just start redrawing that picture. And by the way, when you're doing block diagram reduction, you'll find that you need quite a bit of paper, because you're constantly redrawing these blocks. Okay, so I'm going to go ahead and move that summing junction to there, and I'll just stick in our G2 and our G3, which of course will combine very nicely into series. And then let's see, make sure I get these plus signs. And then we have this pick-off point, and it's going to go into some kind of block that goes here. And to maintain these signs, this one's a plus, that one's a minus. Okay, so what I've done is I've moved this summing junction and I hopped over that block. And so that means that we need this to be 1 over G2. I need it to be 1 over this block. And when in doubt, you can always convince yourself that that is correct, because if I look at this signal right here, I see that I have R coming through there, and it's at the downstream side of G2. If I take that same path here, I get R times 1 over G2, so R over G2, and there's a minus sign, that's fine, and then that gets multiplied by G2, so they cancel out, and lo and behold, at this point I just have R from this path, just like I do in this one. So it's just a quick double check that indeed that is correct. Okay, I'm out of room, so what I'll do is I'll just scoot down a little bit so we can look at that while we redraw this once again. And now what we'll do is focus on these two pieces at the same time. That first piece I circled, even though I have the two summing junctions broken out, it's really just the sum of those three signals. That is, we have an R coming in here. It goes into a big block that's equal to G1 plus 1 minus 1 over G2. And then we have this series block, G2, G3, going to Y. Now, I did something here that I haven't talked about yet. Let me switch to red. This line became 1. The way to think about that is that whenever you have a line where there's no block inserted into it, which could be a transfer function or a gain, then you can think of it as having a block in there that just has 1 in it, and hence the 1 there. Okay, and we'll do just a little bit more simplifying, and let's see, I'm going to go let's see, to there. Okay, so just a little bit more simplifying and we'll be done. We'll have our closed loop transfer function. What I'm going to do is I'm going to take each of these blocks and write them as functions where I have a common denominator. So here I get a G1, G2 minus G2, or I'm sorry, plus G2 minus 1 over G2. And here I can leave these as G2, G3. I have these two blocks in series. I could write them down and cancel things out, but I can see right now that I can cancel that out. And so my closed loop transfer function is then G3 times the quantity G1, G2 plus G2 minus 1. And I believe that's exactly what we obtained just from observing the original block diagram. It's pretty rare that you can just eyeball a block diagram and write down the transfer function, unless it's that canonical form. But in this case, we were able to, and that provided a nice check for that answer. Okay, so in summary, we just went through some terminology, a host of different block diagram reduction techniques, series and parallel, moving pickoff points, moving summing junctions, and then applied them to a fairly simple problem. There'll be another video, as I mentioned before, posted that has a more complicated problem that covers all the bases, but this should get you started. So again, my name's Gordon Parker from Michigan Tech, and thanks for watching.